Sure. Hello, everyone. Today, I want to share a story about how simple configuration change solved one of our biggest performance challenges. Have you ever wondered why your lazy application suddenly slow down during traffic spike, even when your database and external API calls are fine? Let's dive in. I'm Shin and work at stores in Japan. I go by Shia online, and my favorite Ruby library is coverage. I previously spoke at RubyKaigi to 2019 about cleaning up a huge Ruby application, where I show how we use Ruby 2.6 one-shot coverage feature to detect and remove that code in production. So to provide comprehensive digital transformation support service for small to large-size business, among our services, we have a product called Storage Net Shop that allows easy creation and management of online stores such as Shopify. And one of our features is scheduled sale, which allows sales to start at a specific time. And this is where our story begins. Scheduled sales are particularly challenging because traffic depends on many factors. What's being sold, the time of day, and marketing campaign, and whether something goes viral. Most of the traffic arrives within seconds of the sale starting, and this makes traffic pattern not just difficult and nearly impossible to predict. Let me show what we're dealing with. This was our biggest traffic spike last year, a limited quantity product drop at 10 a.m. Look at this pattern. Traffic ramped up just before lunch, and it exploded at exactly 10 a.m. and returned to the normal within 5 minutes. That's a 10 times traffic increase in a second. Our goal is to maintain stable response time with this spike. But as you will see, we weren't quite achieving that. Here is the latency graph from the same product drop, but this is a 2023 version measured by Database API, where we handle most requests reasonably well, but look at that P90 latencies. It spikes to several minutes. This means at least 10% of customers of target store experience severe degradation. Imagine waiting more than 5 seconds just to add an item to your cart during this limited sale. We have to fix this. So our mission is become clear. Deliver a stable purchasing experience even during massive traffic spike. Effortlessly. To handle traffic spike effectively, we identified two key challenges. First, minimize request queuing. This wait time, the gap between receiving a request and actually starting to process it, is purely dead time. So we need to keep this as short as possible. Millisecond here is wasted. Second, fix the latency degradation I just showed you. If we could solve this, we will not improve our customer experience, but also increase our server throughput. Let me quickly outline our infrastructures for context. We run on AWS ECS Fargate with auto-scaling group, managing the number of ECS tests because we have low traffic at morning and high traffic in evening. The application is Ruby on Rails, and at the time we were using Unicorn as our web server. I think this is quite a pretty standard setup, but could you raise hands who are using Unicorn now? No? No one? Then how about Puma? Wow. So in this place, Puma is Unicorn is not a pretty setup. Yeah. Okay. Back to our challenge. To minimize wait time, we need enough workers ready before the sale starts. But how many is enough? Because we can't predict traffic accurately, so we rely on historical data. For example, let's assume last year a New Year's sales makes 5 times spike, then we prepare for at least 5 times spike this year. If actual traffic peak exceeds our estimates some queuing is inevitable. As you saw earlier, most traffic spike peak within 1 minute and resolve within 5 minutes. Auto-scaling group, it detects spike and launch new workers and passing health check, then they finally self-sync. This process takes at least 2 minutes, so it's far too fast for AWS auto-scaling group to help. Ideally, we'd have tuned tune capacity for each cell individually, but this traffic spike happen many times every day, so handle these all cases operationally expensive, and also it's hard to predict how we need. Instead, we overpresent constantly and use that buffer to absorb 3 times small spike. Then there is no spike, then extra capacity is just weight physical. So we launch these ECS tests with Fargate spot it to control cost. But some sales are just too big to our buffers, so like the spike I just showed earlier. For these mega events, for most cases, we can usually identify in advance. For example, Nature Owner let us know about the sale because they don't want to submit stuff at the sales. So we can manually scale out just before the launch based on historical data exists or the traffic prediction gamble begin. Let's dig into the main issue, latency degradation. What exactly was happening? This Datadog APM trace break down the request processing time into components. The blue layer on top is Ruby processing time. Notice how it exploded about 9:59. Meanwhile, database and external API call, the other colors increased slightly, but it makes sense because given how heavy purchase projections are. So this was our first clue. The problem wasn't in infrastructure or the external data dependencies. Ruby itself was slowing down, but why? This is what puzzles us. Ruby slowed down on its own, and it only affected some requests, not all. If it was a code issue, we could see some bias latency for endpoint, but it didn't. If it was infrastructure, we would see some database metrics, but it's not. So this selective slowness suggests something what was some worker code. Let me explain what code workers means here. Large application have many things to execute only once or a few times after boot up, such as establishing TCP connection or building in memory caches, or if you use YG, then there should be JIT compilation and define some method by method mixing and action build template compilation and more. What are heavy lifts? A code worker handling its very first request could be slower than a one. If you're curious about what happened in your application, you can track most of these except JIT and using coverage library. Boot up the application with coverage start and clear its data, and then take coverage lister after processing some requests. Actually, this release is written based on our application startup coverage too. So it's quite funny. So please try actually what your app actually does on startup. So okay, back to the story. So we know lazy app can be slowed like after startup. So, but here is the question. So most of the case we do our scale out at least 30 minutes before the sales start. There should be plenty of time to warm up. So why were some workers still cold? Let's do a simple experiment to figure this out. We will track which unicorn workers actually handle requests. Here's our setup. An endpoint with 100 millisecond response time and 8 workers and just 2 concurrent connections to simulate low load and running for 10 seconds. Let's see how many each workers handle. How many requests each worker handle. Here is the result. worker 0 and 1 handle almost everything. In production, with higher load and different processing time per endpoint, you'll see slightly better distribution, but I'm sure some workers still be idle. What caused this imbalance? Here is quick background. Unicorn is a pre-prog web server, and it created multiple worker processes at startup, which actually handle requests. The quick question is, how does it decide which worker get the next request? On Linux, it uses if poll to handle requests, so it will choose which worker get the work. Let me visualize what's happening. Here's the worker queue from employee's perspective. This grammar it's not an accurate one, but enough to explain the situation. It shows the timing worker 0 finishes the request and tries to back to the queue. Notice that it goes back to the front of the queue, not the back. Yeah, it works more like a last in and first out, not first in, first out. The most recently used worker get the next request. So now our experiments make sense. With just 2 concurrent requests, worker 0 and 1 just jumping to the front, handle everything while other wait forever. Here's what we think is happening. We overprovision for traffic spike. These extra workers sit idle since startup because of unicorn RIF behavior. When the seed sales hit, cold workers suddenly get work. Being cold, so they process requests slowly. So misery solved. If our hypothesis is correct, we need all workers to warm up for the cell to avoid the latency degradation. But how? Using real traffic won't work with unicorn's RIF bias, so pre-warming during deployment is quite expensive and it takes quite more time. We could switch it to Puma traces-based model, but that means ensuring trace safety across our entire code base at 12 years old Ruby laser application and massive undertaking. There must be a better way. This leader is Pitchfork. It's Shopify's fork of Unicorn, and it has a feature called Leapwork. So what's this Leapwork feature? Basically, it takes a worker that already processed a bunch of requests. And use it as a template to recreate all the other workers to reduce memory usage by maximizing shared memory with copy and write. Let's look at how this works. Unlike Unicorn, Pitchfork fork worker from something called the mode. When a worker processes enough requests, most cases worker 0, and it gets promoted to become to a new mode. Then Pitchfork kill all the other existing workers and refork fresh one from this mode. By doing this repeatedly, anything can be shared like decompiled bytecode and moves into the shared memory. This is how Pitchfork save memories, but here's what really matters for us. Refork workers inherit the mode state, such as decompilation and wound up cache, things initialized lazily. So, in the other word, Pitchfork makes all workers be warmed up. So, this looks quite promising, so we decide to give it a shot. I don't tell the detail about how we did it, but because the config migration is simple, but testing is hard, which depends on your application code. So instead, I will provide some caveat. First, forking process in the middle of its life cycle could break things. Forking process inherit its file descriptors, so we need to check it handled properly or not. Background thread can cause issues. You need to verify fork safety for your entire stack, but don't worry, which is much easier than verifying thread safety. If you're using Unicorn already, then might be okay because typical Unicorn configuration has clean up file descriptor phase in before fork or after fork callback. So what you do is just to migrate it to proper place. and except some case. So, for example, grpstem or RubyBeepstem and more. The the Pitchfork repository has excellent documentation for fork safety, so definitely read it before introducing it. So now talk about the fork after. This is the configuration option of Pitchfork, and here's the explanation from document. And it set the number of request threshold for triggering an automatic refork. The limit is for workers. For instance, with refork after 50 in array, a refork is triggered once at least one worker processes 50 requests. Each element is a limit. Each element is a limit for the next generation, 50, 100, and 1000 in array. A new generation is triggered when a worker has processed 50 requests, and then the second generation when a worker from a new generation processes an additional 100 requests, and finally after every 1000 requests. The fork is quite heavy since it spawns processes. So finding proper fork after configuration is quite important. In our case, again, we scale up 30 minutes for sales. So when we want to be triggered refork, traffic to each worker is minimal. So we need to refork to happen during these quiet periods, not after the sales start. This means we should set a small number so refork trigger quickly with just few requests. Finally, let's talk about the worker killer. When you're using Euruko, we typically use Euruko worker killer to manage memory usage. Naturally, we want to do the same thing for Pitchfork, but there is no Pitchfork worker killer. So instead, Pitchfork provides an after request completes, it works name as it is, and which let us implement the same functionality ourselves like this. So, time for the result. This metric compares the same annual product graph and 1 year apart, which I showed before. So, the only significant change is switching from the Unicorn to Pitchfork. Same code, same infrastructure capacity, such as ECS task, the number of ECS tasks. And all graphs use identical y-axis scale for each comparison. First surprise, 2024 traffic was 3 times higher than 2023. Remember, the traffic precision is really hard. And look at 2023 graph, see those gaps? That is when all workers was completely exhausted by slow processing times, so Appen couldn't even start to record the data. How about 2024 graph? Smooth as silk. Despite 3 times traffic, no gaps and no overwhelming workers. How about latency? In 2023, P90 and P95 exploded to several minutes, but 2024 minor bump with 3 times than 2023. Let's check the breakdown. This tells the whole complex story. Reprocessing time exploded in 2023. It barely grew at all in 2024. No more cold workers and no more latency spike. But the most important is customer experience. Here is some reaction from customers who buy the things on that sell in 2024, which is translated and anonymized. So wasn't it a bit right? I was able to buy it super smoothly. It was so smooth that I wondered what was going on until last year. It loaded so quickly that I like, did I the date and the time wrong? By the way, you might wonder, Pitchfork climbed the same memories to shared memories. So did we see that benefit too? Sadly, the answer is no. NetShop always had idle workers, and which make this less efficient, in my opinion. Or perhaps our app doesn't have much things to share after warming up. We didn't investigate it deeper because our goal is improving latency and not saving memory. So this how we conquer massive traffic spike with Pitchfork's Pitchfork feature, a simple, elegant solution that just works with small changes. Most of the case, you might not need this level of optimization, especially with Puma, if you're not using cluster mode. And, but if you're seeing similar pattern in your service, Pitchfork is definitely worth exploring. Last, here's the funny timing story. We did this work last summer, 2024 summer. Then the spring viral Pitchfork's author published a post explaining how he built, why he built it. He mentioned the exactly same warm-up benefit we discovered. It wouldn't be nice to have that post 2 years ago. If you want to dive deeper into Pitchfork design philosophy, I highly recommend reading his article. Thank you.
Wait. Chat.